The purpose of this lab is to better understand the aspects of circuits involved is the node rule, the loop rule, and Ohm's law. General assumptions we took into account are ignoring resistance for all aspects of the circuit. And at the end, our lab result is looking at the CCK value. At the beginning of this lab, we'll look at our circuit that consists of 2 batteries and 2 resistors, as well as 2 ammeters, and at these various points, we'll predict what the current might be. We are able to show that our prediction is right using calculations. Through experimentation, we can prove that ammeters read the same values forward and backward. For this next part of the lab, we took one of our ammeters and replaced it with a voltmeter, and we took the measurement there. Our voltmeter reads 3 volts and our ammeter reads 0 amperes. Our reading is the result of the potential difference and the conservation of energy, because from our 2 batteries, the potential difference results in the positive 3 volts. And specifically about voltmeters is that they become parts of the circuit, and their resistance in turn can alter the circuit readings as well. On to ammeters, we observe how there's a 0 reading, and that's because no current is flowing while it's disconnected, and it reads like the current that's flowing. At this part of the lab, we go through different parts of the circuit and we sum up the potential difference. By doing this, we can prove Kirchhoff's loop rule. In this diagram on the bottom left, we show how the potential differences add up together. Line represents the slope of the potential difference, and we can see how when they add all together up, they end up being 0, proving Kirchhoff's loop rule that in one loop, all the potential differences will sum up to 0. On the right bottom part of this picture is just a reminder of which parts of the potential differences we're going from point to point for. In the following part of the lab, we decide to replace the voltmeter with an ammeter in parallel with the 100 ohm resistor. Now what occurs here is very important. This is where the phrase path of least resistance comes into play. Current likes to follow the path of least resistance, and because we're adding another pathway, we're reducing the resistance, and in turn, using Ohm's law, when resistance is reduced, the current is increased, and we can observe this in the picture above on the right. On the top left of the slide, you can see how we use Ohm's law to calculate these various resistances. For this aspect of the lab, we'll repeat it twice, once with a 10 ohm bulb and once with a 20 ohm bulb. In our circuit, we'll also have a battery and a capacitor. With our 10 ohm bulb, we found that it took 7.5 seconds to charge the capacitor, and the light shined for 7 seconds. When we were discharging the capacitor, it took 11.5 seconds, and the light shined for only 6 seconds. With our 10 ohm bulb, it took 5.5 seconds to charge the capacitor, and the line shines for 12 seconds. When we were discharging the capacitor, it took 22.5 seconds, and the line shines for 11 seconds. Now, when you first connect the battery to the capacitor of the 10 ohm bulb, the capacitor was charging. So you can imagine a capacitor as 2 buckets of water, and charge is building it into one bucket, or the electrons are being forced onto one side. And when you remove the battery from the circuit, the capacitor begins to discharge, meaning that the water starts to even out, and the potential difference tries to eliminate itself, especially getting rid of the charge disparity. It's important to note that a pattern we noticed here is the higher amount of ohms, or the larger the resistance, the longer it takes to charge and discharge a capacitor. For the part of the lab where we were focusing on time-dependent voltage across a discharging capacitor, RC circuits, we took a circuit with a 9-volt battery, a capacitor, and a 30-ohm light bulb, and we measured the voltage over a period of 20 seconds, pausing at intervals to record data. Then took this data and we graphed it. We didn't graph time versus voltage. Instead, we graphed time versus the natural log of delta V over delta V naught. This resulted in us getting a linear line. Once we finally graphed our data and obtained a line of best fit, we obtained our equation to be y equals negative 0.167x plus negative 0.0158. At the beginning of our lab, we know that our actual CCK value would be equal to 6, or 30 times 0.2. So looking at our y equation that we obtained, we're going to solve for our RC constant that should be close to 6 seconds. To solve for our CCK value, you can see how in the calculations on the left, we simply did negative 1 over the slope, and we obtained our CCK, or our constant, as 5.988 seconds. As we can see, 5.988 is very close to 6, and we can demonstrate this by calculating the percent error to be 0.1996%. A good way to better understand something is through hypotheticals. If we were to use a real ammeter in real life, a real ammeter would have more resistance, leading to a lower current reading because we could use Ohm's law, which is voltage over resistance. If we were to use a real life battery in real life, initially it would be quick but slower over time. As the battery got weaker, the pace at which the capacitor would charge would get slower and slower. All circuit components have an aspect of resistance. In conclusion, we can say that we fulfilled this lab's general purpose, which is to better demonstrate how capacitors, resistors, batteries, ammeters, voltmeters, and light bulbs operate by various scenarios using a virtual circuit.